Okay, so polar coordinates in chapter 10, section 7. Basically, your entire mathematical career so far, you've used rectangular coordinate system, which is the ordered pair x comma y. We go on the x-axis, x units. We go on the y-axis, y units. And then we have that ordered pair that we locate. So that looks like this, x-axis, y-axis. Maybe I'm looking for the ordered pair 3 comma -4. So I go to +3 and then down to -4. And I have my dot right there, okay? So that's rectangular coordinates. Now, that's not the only coordinate system that we can use. There are several, actually. The one that we want to talk about today is called the polar coordinate system. So the polar coordinate system looks like this, basically. We have an origin, so if you were to do this, we still have this origin, also known as a pole, and it will be called O, just like regular origin. We also, though, have a polar axis. Our polar axis acts like the x-axis does in the rectangular coordinate system. So this is our zero angle right here. Polar coordinate system requires an ordered pair, just like normal, but it's r comma theta, and theta is the angle that we have turned through to get to the location where the radius ends up, okay? So r is the directed distance of O to P. So if I have some point P right here, maybe, then the radius is that distance right there. Now the theta is the directed angle from the polar axis. So whatever this angle here is from the polar axis around to that angle right there, that's our theta. And we can talk about theta in degrees, or we can talk about it in radians. Most of the time, like for AP calculus, that exam, it's going to be in radians, which is fine. Sometimes you can talk about degrees as well, though. So we need to know what the radians are. So if I have 0 sitting here, we know that there's 2 pi radians in a full circle. So this is also 2 pi. Now halfway around the circle would be half of 2 pi. So this one's pi. And halfway to pi would be pi over 2, so this is pi over 2, okay? As I turn this angle through from the polar axis, the positive x-axis basically, then I'm going through pi over 2 radians, and then pi radians, and then down here 3 pi over 2, until finally I'm at my 2 pi radians all the way around the circle. So we got to keep that in mind, because we're going to be using radians as we assign angles to these polar coordinates. So we can use polar coordinates in mathematical modeling as well as in practical applications. So I'm going to give you a couple examples of a practical application of polar coordinates so that we have an idea of why. So a Ferris wheel and a construction crane. So most of you have probably seen a Ferris wheel before. This center of the circle right here would be the pole or the origin. And then we would have the x-axis directed this way, so that is our polar axis. And now this thing is going to rotate this way so that we end up generating a positive angle theta, okay? So this would be my radius right here, and then I have this angle theta that I've turned through at this point. So we could call that in degrees, maybe it's 30 degrees. Maybe in radians, it would be pi over 6 radians, okay? So that's the idea. Anyway, the point right there would be like that car on the Ferris wheel. So we can define the position of a car on the Ferris wheel using polar coordinates very easily. Now, the construction crane is something that maybe you haven't seen before. I chose to show you this one because it is very like polar coordinates. A typical standard crane that you would see at a construction site that isn't a permanent tower like this one is also using polar coordinates, and here's how. If you imagine like a circle around this crane, then the construction company will deliver some material, whatever that material might be. It could be like an air conditioning unit or something like that. And so they will, the construction company will tell the delivery driver to drop that at a certain position. So what happens is the crane operator knows that that right there is his radius, and then this angle that he has to turn to get the crane to go over the top of that object is his angle theta, okay? So that's basically how that works. Then he'll take this guy out to the correct radius, drop the little attachment or hook or whatever it is down, pick this thing up, and then maybe the building is sitting over here. Maybe it's supposed to go to the top of that building. I drew that way too tall, but it doesn't matter. You get the idea. So he picks it up, and then he spins it around and deposits that thing in the correct location. He knows the correct location because the way that the blueprints are made out, everything is in terms of his crane. So he's going to have a radius to that position, and he's going to have an angle from the polar axis. So if this is the polar axis right here, he'll have an angle that he has to turn to. Once he gets to that angle, he knows he's in the right spot, and then he can go ahead and drop it off. So that's how like a practical use of polar coordinates happens in the real world. We totally use these all the time. And it's kind of surprising that we don't need to teach it anymore, supposedly. So here we go. If I want to plot points on the polar coordinate system, so if you imagine that crane that I was just talking about, that tower would be sitting right here at the origin, and then the boom comes over and picks up that thing right here, and then he's got to drop it off maybe right here on the building, so then he just spins around and lands there and then sets it down. Okay, so that was the idea. Now, we don't want any of that stuff on there. We have our polar axis right here, so this line is where we start all of our angles from. That's our polar axis. So now we're going to turn an angle theta through that. Counterclockwise is positive. We have to remember that. And basically, what I want to show is I'm supposed to use the given angle. Remember, this is r comma theta. I want to use the given angle and then the radius to plot my point. So let me get rid of this arrow right here so it's not confusing us. And for this guy, we have an angle of pi over 3. So we need to remember, I just realized that this is reversed. That's interesting. Okay, so we need pi over 3. So basically, if this is pi over here, this is 0 over here. Okay, half of pi is pi over 2 right here. And then halfway from pi to back to 0 or 2 pi is 3 pi over 2. So I'm just fixing this because somehow the image is reversed. All right, now, if I want pi over 3, which is what this angle is talking about, then what I want to do is go from pi and divide from 0 to pi into thirds. So this might be 1/3 and this is 1/3. So I have this now divided into thirds. So this is pi over 3 right here. This is 2 pi over 3 right here. Okay, so 1 pi over 3, 2 pi over 3, and then pi is actually 3 pi over 3. So we know we probably did that right. Okay, so now pi over 3 is my angle. So I'm looking at that angle right there, and I have to have a radius of 2. So if I just call this ring 1, and then this is 2, and this is 3, then the segment that I need to draw from the origin is along the line that connects with the pi over 3 right there, but it only needs to be 2 units long. So there is my P right there. Okay. So in reality, like this ray here, let me just draw the ray real quick. The ray goes through pi over 3. Okay. And we just needed to go from the origin 2 units along that ray. Okay, so that's the idea. So let me get rid of that so we're not getting confused. Okay, there's my point P there. That is 2, give me a color, 2 comma pi over 3. So we label it. Okay, now the second one is 3 and negative pi over 6. So how do I get to the angle negative pi over 6? You should already know that that just means we go the opposite direction from positive. So positive is counterclockwise. We're going to go clockwise. Pi over 6 units. So now if this is pi over 3 here, then halfway to pi over 3 makes pi over 6. And I'd be doing the same thing on the other side. So here's pi over 6, right? Actually, that's 11 pi over 6, but since we're going the other way, it's actually negative pi over 6. And then this one here would be negative pi over 3. But really that would be not that. That would be what? 3 pi over 2. So that's 12, 6, 9, 6. So this would be 10/6, which reduces to 5 pi over 3. So that's really what this one is right here, 5 pi over 3. Okay, anyway, the point is, with this negative sign right here, we need to be going in the clockwise direction, pi over 6 units. So that means we're going to be following along this ray right here. I want my radius to be 3 units long, so that's going to be on the 3 ring right here. That's my point, and I'm just going to label that 3 comma negative pi over 6. Okay, so that's how you do these. So let's try 3 comma 11 pi over 6. Well, where is 11 pi over 6? Well, it's actually, if you know that 12 pi over 6 is 2 pi, it's actually in the exact same spot. So this ordered pair right here is also 3 comma 11 pi over 6. So that same point counts as 2 different ordered pairs in the polar coordinate system, which doesn't happen in the rectangular coordinate system. Okay, how about 2 comma 3, negative 3 pi over 4? So I need to go in the clockwise direction 3 pi's over 4. So here's 1 pi over 4 right here. Here's 2 pi over 4 right here. 3 pi over 4 would be right here. And the radius is supposed to be 2. So along this ray that goes through negative 3 pi over 4, did I do that right? Nope, totally did that wrong. This is positive 3 pi over 4. Sorry about that. Let me get rid of that. And get rid of these dots. And here we go. So 3 pi over 4 should not be more than 1 pi. And 1 pi is sitting right here. That's kind of how I knew I did that wrong. So 1 pi over 4 is right here. 2 pi over 4 is right here, because that reduces to pi over 2. And then 3 pi over 4 is actually right here. Sorry about that. So we go here. And then we have a radius of 2 units. So we go 1, 2 to the 2 ring right here. That's my point. And we have 2 negative 3 pi over 4. And we're done. So that's how you land on one of these ordered pairs in the polar coordinate system. All right, so in the rectangular coordinate system, each point has a unique representation, like 3 comma negative 4 can't be any other point but 3 comma negative 4. However, in the polar coordinate system, like I just showed, that's not true in the polar coordinate system. So if I have r comma theta, whatever that theta is, I could go around the circle again and land on the exact same spot with the same radius, and that would be considered another location, but it's the same location with a different angle that we talked about. So an example of that might be this. Here's my polar axis right here. If I go, let's just use something simple, 90 degrees, that way I'm not going to screw it up. So we get to 90 degrees, that's sitting right here, okay? Now that radius, whatever that radius is, just for example, let's say that the radius is 3 units. So that's my point right there. Now if I go 90 degrees, which would be pi over 2, so I'd have pi over 2 plus 2 pi. Well, the 2 pi takes me all the way around the circle once, and then to pi over 2 again takes me right back to the same spot. Okay, so these are coterminal angles, which means we have the same position on our polar coordinate system. So that's what that's trying to say. Now, the other thing is we can actually call a radius negative. So the interesting that happens there, let me get rid of those, is if I said I had a positive radius like I do right here. So let's just make something up. We have a positive radius of 2, let's say. So I'm at some angle right here. Here's my positive radius of 2. Whatever that angle is right there, let's call that pi over 3, okay? So we're at pi over 3 for our angle, and our radius is 2. Now, I could say I have a negative radius, and all that does is it switches the direction that I go. So rather than having a radius that went from the origin to the point, I could say I had a radius that went the other way. And if my arrow is going like this, and I move that arrow to the origin, so now this is the origin, then my radius of 2 now is kind of reflected, and it's going the other way. So now this would be my negative radius, okay? But now r comma theta, so this was 2 comma pi over 3. I could have negative r, which put me right here, but then if I add theta to that, if I add to that theta, sorry, pi, that takes me from here and moves me pi this way. And that puts me right back where I started at 2 comma pi over 3, okay? So I can consider a negative radius, which just reflects the direction I normally would have gone, and then I could add a full pi radians to that and put me right back where I started. So let's get rid of these and talk about those 2 examples sitting right there. So what do? We have plot the point and find 3 additional polar representations of the same point. So let's first plot the point. So where's negative 3 pi over 4 at? So I'll do this one without screwing up this time. I'm going negative 3 pi over 4. So from 0, I go negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4. So I'm along this ray. And now I have to have a radius of 3. So that is on the 3 ring right here. So that's my point, 3 comma negative 3 pi over 4. So now the question is, I need 3 additional polar representations of the exact same location. So how do I do that? Well, I can do the obvious one, which is go in the positive direction instead of the negative direction. So I would still have the same radius of 3. And then I just got to figure out what this angle is that I turn through right here. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So I could call it that. Okay, that's just going in the positive direction. So now, what if I did something different and I went around the entire circle twice? So it would still be a radius of 3. And now I'm going around fully 2 pi plus this length right here, or this angle right here, which is another 5 pi over 4. So 2 pi turns into over 4 would be 8 pi over 4, comma 5 pi over 4, or not comma, sorry, plus. And then my answer then would be 3 comma 5 plus 8 is 13 pi over 4. Okay, so I have my radius is the same. I have a new angle. I went around the circle 1 full time before I went the 5 pi over 4. And now I need one more. So maybe we take the radius. Let me get rid of these drawings that I have on here because they're going to confuse me. And maybe I take the radius and I go the other way with it. So I put on here a negative 3 radius, which puts me right there. Okay, so now my radius is negative 3. So from here, I would be at pi over 4. And I need to go a full pi around to get to the correct position. So where am I then? This is pi over 4 plus a full pi, which makes what? Don't know. Nobody knows? It is just pi? 5 pi over 4? I don't know. What is it? So the way that we need to word this is because it was supposed to be here, and instead I drew it here, that gave me the negative radius, but it is at pi over 4. So it is negative 3 comma pi over 4. If you think of it this way now, if I go to pi over 4, I'm going to be along this ray. But since I said negative 3, that reflected that arrow that I was going to draw to here. It's reflected, and now it is pointed this way. Because of that negative 3, it reversed the direction of the ray. So we go to pi over 4 first, reverse the direction, and now we're in the correct direction. Okay, so that's the idea behind that one. So let me get rid of all of this stuff, and then we'll try the negative 1 comma pi over 3, just to try to let this sink in, because I know that probably was a little confusing the first time you saw it. So here we go. We need negative 1 and pi over 3. So first thing I'm going to do is I'm going to make my ray for pi over 3. Pi over 3 is right here. So now I have my ray. Normally I would be along that ray, but the radius is negative 1. So I'm going to reflect this ray. So now I'm going this way, and I need to be a radius of 1. So that's going to put me right there. Once I reflected it, now I have this ray right here, okay? So that is the position negative 1 comma pi over 3. The pi over 3 is right here. I reflect it for that negative 1, and now I have the correct position. So now we need 3 more that match this ray that I just drew. So what could we do? Well, we can say, what if we just did it normal and we went around to here? So what angle is that? If this is pi over 3 right here, then we have 3 pi over 3 to get around to here, and then another one right there. So that makes 4 pi over 3. So I could say I have a radius of 1 at 4 pi over 3. So that's 1. I need 2 more. I could do this way. So that would still be a radius of 1. And how far did I go this time? If that's 4 pi over 3, then I had 2 pi over 3 more to go. So that would be negative 2 pi over 3. By the way, being very good at the unit circle is very helpful here. So if you're not solid on the unit circle, there's ways that we can get you to really understand the unit circle kind of quickly. So we'll try to do that sometime. All right, so we have these two. Now I just need one more. So what could that be? Well, let's see. If I did a negative 1, I kind of already did a negative 1 with that pi over 3. So what could I do instead? Let's see. Maybe I don't want to do a negative 1. That'd be too complicated. So let's get that out of there. Let's do a positive 1 and do something different. Let's go in the positive direction around the circle twice. So we're going to go around 1 full time to here. So that's 2 pi. And then, so 2 pi plus, and then again to 4 pi over 3 to make that coterminal angle, so plus 4 pi over 3. So now 2 pi turns into 6 pi over 3 plus 4 pi over 3, which makes 10 pi over 3. Okay, so that's 3 alternatives to the exact same position in polar coordinates. And so the point of this is just to show you that you can have multiple ways to represent the same ordered pair in the polar coordinate system as opposed to the rectangular coordinate system where you only have one way to represent a unique point. Okay, so we can convert from rectangular coordinates to polar coordinates as well, and then also vice versa, by just using basic trig. So what we need to do is just recall what these trig functions actually represent. So let me start something here, and I'm just going to draw something out to there, and here's my point. So now if I drop this down, what I'm doing is I'm making a right triangle. So I have turned my angle, this is my polar axis over here, okay, so this is 0 for theta. So what I've done is I've created an angle theta in the positive direction, okay, so this is my reference angle. We know from geometry that sine is the opposite, so this is the y height of that triangle, over the radius of the, so that's basically the hypotenuse in geometry. But now because we're talking about a circular coordinate system, we need to be talking about the radius. So the hypotenuse here is the radius, and then the distance from the origin to the x, in the x direction, how far I went, that is x, okay? So now the trig functions, SOHCAHTOA. Sine is the opposite over the hypotenuse. So the opposite side of the reference angle theta is y divided by the hypotenuse, which is r. So sine theta equals y over r. Cosine theta, so cosine is the adjacent over the hypotenuse. So the adjacent side is the one that's touching the angle, and that's this guy, x, and divide that by the radius. So we have x over r for cosine theta, and then tangent theta is y over x. It's the only possible other combination of sides of the triangle. So that's y over x, the opposite over the adjacent, TOA. Okay, so we remember those from geometry. Now to convert from polar to rectangular coordinates, the coordinates that we're looking for are x comma y. The x coordinate will come from r cosine theta. How come? Because if I take this equation and I solve for x, multiply both sides by r, then these r's are gone and you're left with just r cosine theta. Okay, so that's where that comes from. And the same thing comes from this y equals r sine theta, multiply both sides by r, and you wind up with, those are gone, y equals r sine theta. Okay, so that's how that comes about. All you have to do is know the angle and the radius, and you can do these two formulas right here to get your x and your y coordinates for the ordered pair in rectangular coordinates. Now, if I'm in rectangular coordinates and I want to switch to polar coordinates, I can get my angle theta. Because I know the ordered pair xy, because I'm in rectangular coordinates, I can use tangent. Tangent uses y divided by x. So tangent theta equals y over x. In order to get the angle theta, then I need to arctangent or inverse tangent both sides. And when I do that, these two are inverses of each other. They wipe out, and I'm left with theta here equals inverse tangent of y over x. Okay, so that's how you find your theta. And then because we're dealing with circles, r squared equals x squared plus y squared is how you find the radius. This is the equation for a circle right here, centered at the origin. So if I know the x coordinate of this location right here, and I know the y coordinate, then all I have to do is use this circle equation, and find r. So I'll have to square root both sides. So r equals the square root of x squared plus y squared. And that's how you get your r. And then you have your ordered pair, r comma theta. So that's how we can convert from one to the other, depending on which one we're in. Now, if I want to convert from polar to rectangular then, I want to convert to rectangular coordinates here. So first I find this location. This is my r and my theta, like I can get on my graph right here. And I can say, okay, I have pi over 6. So if there was a circle here, pi over 6 would be kind of along this right here. A length of square root 3 is probably right around there, about 1.7 or something like that. So that's what I'm looking for right there, okay? That location. So I kind of know what that ordered pair is going to be. So all we have to do to convert from polar to rectangular is we're using these guys right here. X equals r cosine theta, y equals r sine theta. Because if I make a right triangle right here, the y coordinate would be that length of the triangle, and the x coordinate will be that length of the triangle. And we already know the radius right here is the square root of 3. So we have the x coordinate is the square root of 3, that's the radius, oops, not r, 3, times cosine the angle, which is pi over 6. So just make sure you're in radian mode. And what do we get? Whatever it is. Y is the square root of 3 times sine pi over 6, which is, okay, so let's figure this out. Cosine pi over 6 is the long side of a 30, 60, 90 triangle. The long side of a 30, 60, 90 triangle is square root 3 over 2. So we have square root 3 times square root 3 over 2, which gives me square root 9, which is just 3. So I have 3 halves. That's my answer for the x coordinate. Now, for the y coordinate, we have the square root of 3 times sine pi over 6. So pi over 6 gives me y. The y side is going to be the short side, and that's just half of the radius, which is, in this case, oh, actually it doesn't matter. It just winds up being 1/2. So we have square root of 3 times 1/2. So that makes root 3 over 2. So now we can write our ordered pair. It is the x coordinate, 3 halves, comma, the y coordinate, square root 3 over 2. And that's my answer. Okay, so now rectangular coordinates to polar coordinates. So let me just go back real quick and remind us what rectangular coordinates to polar looks like. I have to find theta using tangent theta equals y over x, and I have to find r by using the circle equation. So I go back to here, and now negative 1, 1 is where? Negative 1, 1 is right here. Okay, so I want to find my angle theta. So tangent theta equals y over x. The y coordinate is 1. The x coordinate is negative 1. So that is just negative 1. So then I do inverse tangent both sides. Theta equals of negative 1. And we get, where are we? So we are at 3. So if this was a circle, right? 1 pi over 4, 2 pi over 4, 3 pi over 4. That's where we're at. So this is 3 pi over 4. Now I got to figure out my radius. So r squared equals x squared, so that's just 1, plus y squared, so that's just 1. So I have 2. So I square root both sides. R equals the square root of 2. So then my ordered pair is the square root of 2 for the radius, comma, 3 pi over 4 for the angle. And that's the answer. Okay, so I also asked you to do 0, 2. So let's visualize where that's at first. It is right here. So in this case, because I already know that I turn through that angle right there, that's 90 degrees or pi over 2, I don't need to do the math this time. I already know it's pi over 2. And I already know the radius also. The radius is that distance right there, which is just 2 units. So that's the answer for the second one. Okay, sometimes you can avoid the math if you're visualizing what these look like. Now let me go back, and we had to do another one here, 2 comma pi. So we want to convert that polar coordinate to rectangular coordinates. So where is 2 comma pi? Well, first of all, the angle pi is over here. So I had to turn all the way through pi units, so I'm along the x-axis. I have a radius of 2, so I'm sitting right here. That is my guy right there. Okay, so now I want to convert that to rectangular coordinates. Well, this is really easy because it's already sitting there on an ordered pair. I just call it out. It is -2, 0, and I'm done. So again, sometimes if you're visualizing, you don't need to do the math. But sometimes, like the first example, the math needed to be done because we couldn't quite figure out exactly where all that stuff was. Okay, so let me go back now. We already did those, and here. If I want to convert a rectangular equation to a polar form, so I'm converting the equation that I have that I'm normally used to, like y equals x squared, I'm going to convert that to polar coordinates instead. It's kind of interesting that we can do that with equations as well. So to do this, just replace x by r cosine theta, and replace y by r sine theta, and then simplify. So by simplify, I just mean solve for r. So we have y equals x squared. Y is now r sine theta equals x turns into r cosine theta, but it is squared. It is x squared, so this is squared. Okay, so now we want to solve for r. And we have an issue here. We have two r's going on. So remember that when you have two things being multiplied together, raised to a power, like they have here, we can simplify by sending that exponent to both. So we have r squared cosine squared theta on this side, r sine theta on this side. It's tempting to divide by r here, but that's not what we're going to do. We're going to move this guy over so that we have equals 0. That's how you solve. So we have r squared cosine squared theta. Now I divided both sides by sine, or sorry, I moved these over so I have minus r sine theta equals 0. Okay, so now we can pull out a GCF of r. So we have r times r cosine squared theta minus sine theta equals 0. Now at this point I can use the zero product property. When I do that, I get r equals 0. So if the radius is 0 in the polar coordinate system, nothing's happening. You just have like the origin sitting there. There's no necessarily defined angle, so who cares, all right? So this guy we don't care about. This guy we do care about, r cosine squared theta minus sine theta equals 0. Now solve for r. So this guy goes over. I have r cosine squared theta equals sine theta. And now if I divide both sides by cosine squared theta, I have r equals sine theta over cosine squared theta. So now we're just going to use a little bit of identity here. Cosine squared is really cosine times cosine. So what I have is sine theta over cosine theta cosine theta. Okay, so I can split this into two fractions being multiplied together. I have sine theta over cosine theta times 1 over cosine theta. And when I do that now, I have sine theta over cosine theta, that's tangent theta. And then 1 over cosine theta is secant. So we have tangent theta, secant theta. And that is r. So we have converted now to polar coordinates using r and theta. Okay? Now we don't know what that would look like on the graph, but it doesn't matter. We were able to convert from one to the other using this process. Okay, so now converting polar equations to rectangular form instead of rectangular to polar, it's a little bit trickier. We just have to use a little bit of intuition sometimes. If possible, try to visualize what the graph would look like. So in this one, I have r equals 2. That just means the radius is 2 always. So if the radius is 2 always, then I have this graph. What is that graph? That's a really crappy circle, but it is a circle. What is that graph in rectangular coordinates? Well, it's a circle. So we're going to use the equation x squared plus y squared equals r squared. I know r is 2. That means my real equation here is x squared plus y squared equals, since the radius is 2, 2 squared, 4. And that's my answer. Okay, now let me get rid of this drawing and show you the next one. Theta this time is pi over 3. So where is pi over 3? Pi over 3 is like right here. So let me label that so we know. Okay, now theta is always pi over 3. So that means that whatever I have on my polar coordinate graph has got to look like that. This is a line. So I'm going to have an equation for a line here. I need to know the slope and the y-intercept, and I'll be able to write it in slope-intercept form. So what do I do? Well, we know that theta is pi over 3, and we know we can convert from polar to rectangular by using tangent. So we have tangent theta equals y over x. So what is y over x in this case? So if I just do the conversion that I was talking about before, so let me go back. And where is it? Here. X is r cosine theta, and y is r sine theta. We can use those. So I'm going to go back to this. Now, why did I write tangent? I have no idea. So let me erase that for a second. I do know why, but let me try to explain that. Okay, so if r cosine theta and r sine theta are what we're dealing with, then what I can do is I can say, all right, my theta is pi over 3. So therefore, if I do a conversion here, let's see, if I said r cosine theta equals x and r sine theta equals y, okay, so then y over x creates tangent, right? So I'm going to take this y and divide by this x, and I'll create tangent theta. R divided by r is gone. So I just wind up with tangent theta equals, and now y over x. So great, what does that do for me? Well, let's see. So because I know that my angle is pi over 3, I can plug in, like tangent theta is sine over cosine. So I can plug in and say, what is sine pi over 3? So sine pi over 3 is some value, right? It's like sine, here's my angle theta. This would be the y coordinate here, and that's the long side of the 30, 60, 90 triangle. So sine pi over 3 is root 3 over 2. So I have root 3 over 2 here. And cosine pi over 3, that's the short side of the 30, 60, 90 triangle, so that's going to be 1/2. So that means tangent theta is root 3 over 2 over 1/2. And if you copy dot flip, leave it, change it, flip it, this is 2 over 1 here, and we multiply, those 2's are gone, and you're left with just the square root of 3. So now I have tangent theta equals square root 3 from that knowledge. So what does that do for me? Well, since I did y over x, what you just calculated was actually the change in y divided by the change in x, and that's the slope, which means that this number right here is the slope of that line. So now I can write y equals the slope, which is the square root of 3, times x, but then the y-intercept, because this line goes through the origin, is just 0. So that's your equation right there, okay? Like I said, it is trickier than the rectangular to polar. So we got to kind of be a little inventive here. So now our secant theta, we can try to figure that out by saying, let's see, was that supposed to be an actual angle? No, it's not. So our secant theta, we don't know what that graph looks like, okay? We're not given an angle like we were here. It's just a variable, actually a variable equation. So we have to do some work here. So what we're going to do is we are going to take the secant theta, and we know that secant is 1 over cosine. So I can think about secant theta as 1 over cosine theta. So let's see where that gets us. What we need to worry about then is what is like this equal to. So if I solve for basically, let me get rid of the division here, okay? Sorry. So if I get rid of the division, I multiply both sides by cosine theta. When I do that, then these two go away, and I'm just left with equals 1. On this side, on the left side, I have r cosine theta. Okay, so now I have something I can actually work with. R cosine theta equals 1. R cosine theta is something that I know. It is this right here. That's my conversion between polar and rectangular coordinates. So that means r cosine theta can be swapped, and I have x. X equals 1 is my answer. I've just converted it to rectangular coordinates. I don't have polar anymore. So x equals 1, we know, is a vertical line that goes through 1. So if I get rid of the drawings that I had here real quick, the vertical line that goes through 1 looks like this. Here's one right here. We have a vertical line going through 1. Okay, that's the equation, x equals 1. And there you go. That's how you do it. So it is trickier to convert from polar to rectangular rather than rectangular to polar, but it is possible to do still using the same conversions that we were using before between circles and the relationship between sine, cosine, and tangent and what sides they relate to. And that's how you work with polar coordinates.